Okay, so who really cares about 10-adic number systems or prime-adic number systems? Well, actually, they're really useful for solving and analyzing and trying to solve some unsolved tricky questions in mathematics still to this day. There are so many fundamental questions about multiplication in mathematics, in particular primes and prime factorizations, that mathematicians do not know how to tackle just yet. And p-adic numbers, prime-adic numbers, are a way to do multiplicative thinking that could actually get to some solutions. So they've very much used this 10-adic, this prime-adic number systems in advanced number theory. But I want to share with you right now one really surprising, out-of-the-blue application of 2-adic numbers. That is, base 2 numbers that go infinitely far to the left of the decimal point. It turns out, here's a great geometry puzzle, which goes as follows. I give you a square. Can I subdivide that square into triangles of the same area? And the answer is yes, I can do it for some triangles. So for example, here's a subdivision, if I drew it correctly, of a square into 6 triangles, each of the same area. I could do it with 2 triangles. In fact, if I just drew the diagonal, bingo, there would be 2 triangles of the same area that subdivide the square. Suppose I said to you, 12. Could you subdivide a square into 12 triangles of equal area? Or 28 or something? Interesting. Every answer I gave you, every question I gave you just then, was about an even number of triangles. A real challenge would be, is it possible to divide a square into an odd number of triangles, each of the same area? And you try it, and you try it, and you try it, and you find you can't seem to do it. And in fact, Paul Monsky in the 1970s managed to prove it is impossible to subdivide a square into an odd number of triangles of the same area. Whoa. And the way he proved that result was actually with 2-adic numbers. He figured out a way to label the coordinates of these triangles using a 2-adic number system for the coordinates. Don't use the ordinary real numbers with decimals, use 2-adics instead. And he found if you had an odd number of triangles, you get an inconsistency in the labeling of those vertices, which means having an odd number of triangles was impossible to begin with. You cannot subdivide a square into an odd number of triangles of equal areas. Crazy. And that's the only proof that I'm aware of that result. It had to rely on 2-adic numbers. So who would guess that these weird decimals, well, numbers going infinitely far to the left of the decimal point, actually are connected to a geometry result like this? Mathematics is full of delightful and wonderful surprises.